As you can see, connection, one big piece of metal, connection, one big piece of metal, not connected. If I pop one of these out, you can see that all these little holes go straight into these little metal clips, and that's how you make connections. So that's why it's kind of a bad idea to put multiple wires into the same breadboard hole, because it will really only grasp the largest wire. You might get a faulty connection. Most things like leaded capacitors and resistors go in just fine. Resistors like this skinny leg and they have a perfect connection. If that's the case, just barely pin the entire leg using a soldering iron and a little bit of solder. Just a little bit of extra solder on there.
You should not need to do this. I've never done it, and I don't think you should need to do it.
Just to give it something to grab onto. Most ICs or switches like this, again, through hole only, will go in just fine. You just want to make sure that you really push the body all the way to the breadboard to make sure that those clips can grab onto those legs. You will likely see around, but it kind of rat nesty look. So be sure to change that for shorter, more precisely bent wires when you go to turn it in. It'll really.
And that's what you have. You have a wire pack with pre-cut wires and all that, and that's what you'll be using for build your projects. And so it is a lot neater. You do have to lay out more wire, but it's a lot better.
Impress your professors. Okay,
so
let's do a really quick example here. Obviously not using the row that I just pulled out. So I have a switch in the middle. These legs are not connected. When it's raised, when you press it, all the legs get connected. So what I'm going to do is bring in power, that's my red clip, into this row over here. So this entire row is now steam. I'll take an LED, put the positive lead in that row, and move down into that switches row down a little bit lower.
So when she connected the positive lead here in one of the holes, that left four remaining holes in which she could stick the LED in. It doesn't matter which one, as long as it's one of the four that line up with the positive lead here.
Oh, that is connected into the switch. The switch is not connected. When you press it, it is connected, and I can put another LED, the positive leg, from that terminal down here to another row. And then we will connect that row to ground.
Or negative.
So no soldering involved. When I turn this on, I have it set to 6 volts and 20 milliamps. Make sure you have a current limit on this or you will blow up your LEDs.
You won't have a current limit on most of the power supplies you work with. This is one reason why you need a resistor in there, and you've done that with your first experiment.
Good. Nothing happened. Press the button. They light up. You complete the circuit. No circuit. Circuit. No soldering required. That's the beauty of the breadboard.
Okay. Now, up here, where's everything? Having a little delay here. Let's see what's going on. There we go. Okay, again, always look at my recent announcements. There'll always be 3 here and they cycle through. But on this first one at the top, that's the latest one, I've given you some steps on how to construct the circuit for your solderless circuit board activity here. I went through these steps with a student last night and I've posted them here. So if you still haven't built it, and I think there are only just a few of you, that's okay. Just go, you might want to copy these steps and just 1, 2, 3, 4. Any questions? Okay, then let's go to, we've done this, we've read this. Oh, by the way, of course, you have your Zoom summaries for the previous week. There'll be two, one for Tuesday, one for Thursday, of course. So always read those. Okay, so we've read this, we've looked at this, we've looked at how the solderless circuit board works, as a preview, I mean, a review of what we're doing here. And now I want to take a look at these three things, these three characteristics: current, voltage, resistance. Let's look at the exercise for current. Okay, it's worth 25 points. It has 11 questions, I believe, that I'd like you to answer based on the video that you're going to look at here. We'll look at it now. And it would really be nice if you could get this exercise into me today. If all of you could find some time to just do at least one exercise today. Some of you need the weekend to work. If you can start chipping away at these instead of waiting until Sunday to do them all, you'll feel better and it'll work out better for you. I love to just see them come in, and again, they're coming in great, and you're doing a great job. You know, most of you are going to get full points on everything you do. Not always. I read every question, every answer, and so on. But most of you will do that. The difference between A and B students or C students really is in the number of exercises they complete. So if you're here and completing the exercises, you'll do well. If you start missing exercises or falling behind, that's where we're going to have a problem. Okay, let's see what we've got here.
Can you get me a pen?
Let me see if I can get this in. Okay. Okay, this is an interesting mindset on current. I think it's quite good. It's about 11 minutes. So relax, get your cup of coffee, but let's pay attention and see what current's all about.
Hey there guys, Paul here from the engineeringmindset.com. In this video, we're going to be discussing electrical current. We'll be looking at what is current, the different types of current, how to check the ratings of your electrical devices, as well as how we use safety features to save you from being electrocuted. Current is the flow of electrons in a circuit. To use electricity, we need electrons to flow the same direction around the circuit. We usually use copper cable to form the circuit. The atoms that make copper have a loosely bound electron in their outermost or valence shell, which is free to move around inside the metal. This free electron is very easy to move, which is why copper is so popular. It's so easy to move that it will naturally just move to other copper atoms by itself, but this occurs randomly in any and all directions, which isn't useful for us. For us to make use of this, we need lots of electrons to flow in the same direction along the circuit. We can then place things like lamps in the way of these electrons so that they flow through it, and then they generate light and heat, etc.
So there are conductors in and any metal is a good conductor, and copper wires is a good conductor. And copper wire is a good conductor because it has lots and lots of free electrons already in the wire. They're there in the wire. If you used a rubber band instead of copper, you'd have very few free electrons.
To do this, we need to force the electrons to move, and we can do that by applying a voltage. Voltage is the pushing force. It's like pressure in a water pipe. The more pressure we have, it can flow. The more we have, the more electrons.
And a pulling force. Voltage makes the electrons that are already there in the wire move. And they're like a pea shooter with a bunch of peas in it. If you have 50 peas in it, you put one pea in at one end, another pea tops out at the other end. As we'll discuss later, current flows like a Ferris wheel, not like a choo-choo train. But right this moment, my main point is that the electricity, the movement of free electrons in one direction, those free electrons are already in the wire.
We covered the basics of voltage in detail in our previous video. Do check that out, links in the video description down below. So we need a lot of electrons to flow along a circuit and through our lamps to get them to shine brightly. However, the cable and lamps can only handle a certain amount of electrons passing through them. just like a pipe is rated to handle a certain amount of water passing through it or a certain pressure. If it exceeds this, then the pipe will burst. Likewise, if too many electrons pass through the cable or the lamp, then they will just burst or burn out. We refer to the flow of electrons as current, and we measure this in the unit of amperes, although you'll usually just hear people say amps. This is represented with a capital A. For example, this fuse has a 3 and a capital A, which means it's rated for 3 amps of current. We'll look at how we use fuses later on in this video. If you look on the plugs of your electrical devices, you should find labels from the manufacturers which tell you what the product is designed to handle. For example, this laptop charger tells us that for the device to work, it needs an input of between 100 and 240 volts and 1.5 amps of AC or alternating current. The charger will then convert this to give an output of 19.5 volts and 3.3 amps of DC or direct current. AC and DC are different types of electricity. The plugs in your homes will provide AC or alternating current. In this type, the electrons do not flow in a continuous loop. They alternate between moving backwards and forwards, just like the tide of the sea. Your electrical devices like laptops and mobile phones will use DC electricity or direct current. In this type, the electrons do flow in only one direction, much like the flow of water in a river. We transport electricity from the power stations in AC alternating current and send this to our cities and homes. We use AC here because it can be transported very efficiently and over much greater distances than if we were to use DC direct current. We can also very easily increase or decrease the voltage using simple transformers. We've covered how transformers work in our previous videos. Links down below for that. Do check them out. We mostly use DC direct current in the circuit boards of small electronic devices like laptops, mobile phones, and televisions. That's because DC is easier to control and allows circuits to be smaller and more compact. Many appliances will use a combination of AC and DC. For example, a washing machine will use AC induction motor, which is used to spin the tub with the clothes in. But the circuit board, which controls the settings, the lights, the timers, as well as how fast the motor spins, will use DC power.
Yes.
We can convert AC to DC using an inverter. This is extremely common in electronics. We've covered how inverters work previously. Links down below if you want to watch and learn about that also. People often refer to a river or the tide of a sea as having a strong current. It's very similar to electricity. A river with a lot of fast-flowing water is said to have a strong current. The same with electricity. A cable with a lot of electrons flowing through it has a high current. A river is able to handle a certain amount of water flowing through it. But if more water enters than the river can handle, then the river will burst its banks. The same with electricity. The cable will burst and burn out. Therefore, manufacturers need to be able to test cables and lamps to find out how much current they can handle. We also want to be able to see how much current is flowing through our circuits, as well as being able to calculate this. We can measure this using an ammeter, and we measure the flow of current in the circuit using the units of amps. So what is an amp? 1 amp is equal to 1 coulomb. One coulomb is equal to approximately 6 quintillion 242 quadrillion electrons per second. What does that mean? Another way to look at this is that to power this 1.5 watt lamp with a 1.5 volt battery, approximately 6 quintillion 242 quadrillion electrons need to flow from the battery and through the lamp every second for the lamp to stay on. If we reduce the voltage, then less electrons will move and the lamp become dim. If we increase voltage, then more electrons will, and eventually the lamp will not be able to cope, so it will burst or burn out.
Okay, what they're saying here is that current and voltage are directly proportional. It's almost intuitive, but they're directly proportional, meaning the more voltage, the more current. The less voltage, the less current. And of course, if a light bulb is there, more current means brighter light, less current means dimmer light.
So to measure the current in a circuit, we need to connect an ammeter in series so that the current flows through it. Think of it like a water meter. The water needs to flow through the water meter for us to know how much water is flowing in the pipe. Likewise, we need the electrons to flow through our ammeter so that we know how much electricity is flowing in our circuit. Instead of using an ammeter, we're going to use a multimeter, as we can do a lot more with this device. I'll leave some links down in the video description where you can pick up a good multimeter cheaply. I highly encourage you to get one of these for your toolkit. They're pretty cheap and are very useful. If
And of course, we'll be looking at that one on Thursday.
connect a lamp to a battery in series, then we can measure the current using a multimeter by connecting it in series. If we connect this 1.5 volt battery and this lamp, which has a resistance of 1 ohm, a current reading of 0.5 amps, which means 9,636 quadrillion electrons are flowing through the lamp every second.
Now, you don't have to memorize that. It's just a lot of electrons, that's all. But at any given time, the number of electrons in the wire is the same. For every one that's being pushed out here with the battery, one is being sucked in. So if you had 50 electrons in the wire, you'll always have 50 electrons. Not the same ones, but you'll have 50 electrons.
Because it's in series, all the electrons in the circuit are flowing along the same path. So that the multimeter if we circuit connected, the lamp also has a resistance of 1 ohm, and we are adding more resistance to the circuit, so the electrons are slowed down. In this case, we get a reading of 0.75 amps, which means 4,818 quadrillion electrons are flowing per second. This is in series, so again, we can move the multimeter and we get the same reading. If we now connect the circuit with 2 lamps in parallel, both with a resistance of 1 ohm, and connect this to a battery of 1.5 volts, then in the main wire to and from the battery, we get 3 amps. But on the branch of each lamp, we get 1.5 amps. That's because the path of the electrons has split. So the electrons are shared with some flowing through lamp A and some flowing through lamp B. In example, both lamps have equal resistance, current is split. But if the lamps are of different resistance, then the current is split unequally. For example, if lamp A has a resistance of 1 ohm and lamp B has a resistance of 3 ohms, then in the main wire, we get an amp reading of 2 amps. In the branch for lamp A, we get 1.5 amps, and in the branch for lamp B, we get 0.5 amps. As you can see, lamp B is dimmer because there is a higher resistance, so less electrons can flow through it.
So they're going into a lot of things here that, you know, Ohm's law, they're really talking about that and so forth. We'll get to that stuff later.
In both cases, the amps in the branches will add up and are equal to the total current flowing in the main wire to and from. Now, dimmer because if you also said that cables, etc., are only rated to handle a certain amount of current. If it exceeds this, then they can burn out. So to restrict the amount of current that can flow, we can add resistors into the circuit or into part of the circuit. These act like speed bumps and slow the electrons down. Resistors are like putting a...
Now, he talks about slowing electrons down, and that's not correct. Electrons do not slow down. They do not speed up. There's more electrons and fewer electrons, but the speed at which they travel through the circuit is always the same, and it's pretty close to the speed of the light.
Bend into a garden hose. The kink adds resistance to the flow of water, which reduces the amount of water that can flow out of the hose. Similarly, we can add resistors to the circuit and it slows down the electrons.
What he means is there are fewer electrons.
For example, this LED is rated at 25 milliamps and 3.3 volts, but our battery is rated at 9 volts. So if we were to connect the LED to the battery, it will just burn out because it can't handle that much voltage and current. So to stop the battery being out, we need to place a resistor into the circuit. In this case, we'll use a 270 ohm resistor to bring the voltage and current down to a safe level for the LED.
Now, you've done this already with your solid circuit board. This is basically what you did. And as you increase the resistance, there was less current, and pretty soon you got to the point where the LED wouldn't light.
If you want to see how much current is flowing through your electrical devices at home, then you can use one of these cheap energy meters. You simply plug your appliances into it and it'll measure the voltage, amps, watts, power factor, etc. And you can then even calculate how much it costs to use the appliance. I recommend you have one of these for your toolkit and below cheaply. We saw earlier that we can use resistors to reduce the amount of current flowing in the circuit and protect our devices. Another thing we can use is a fuse. Fuses, in a basic sense, have a thin piece of wire inside them which is rated to handle a certain amount of current flowing through them. In this case, this one is rated to handle 3 amp or 19 quintillion 272 quadrillion electrons per second. The fuse acts as a weak point and is very cheap to replace.
So a fuse is not really a resistor. It's not like that at all. There is a certain amount of current that it will handle. If it's a 3 amp fuse, then it'll just sit there fine up until 3 amperes. If more than amperes is made to flow the circuit for some reason, then the fuse gets upset and it blows. And that's what we want, because if it blows, it's like opening a switch and no current flows, and we don't damage the equipment. So it's an up to thing. If you have a 2 amp fuse, that means it will handle up 2 amperes and then it will get excited.
So if too much current flows in the circuit, it will burn out and open to break the circuit and protect the more expensive electrical components. You can find these mounted on circuit boards, and you can also find these built into some plugs. For example, this plug from the UK has a fuse built into it to protect the electrical device. Another device you've seen these in your home, the circuit breaker. It's essentially a switch that will automatically open to break the circuit if it detects too much current or too many electrons flowing through it.
Basically, a circuit breaker is a resettable fuse. It breaks open just like a fuse does when too much current flows. But then if you correct the problem, you can reset the circuit breaker and start over. You don't have to there's no fuse to throw away and start over.
It's rated to handle a certain amount of electrons flowing through it per second, but it measures this using heat or an electromagnetic field to detect and act on if too many electrons are passing through it. If it exceeds this, then it will open to break the circuit. If, for example, we slow it, detect the slow rising because the current causes it to heat up. As it approaches the design rating, it will break the circuit to cut the power and protect the cables and devices. The load can then be reduced and the circuit breaker reset, unlike a fuse. Another extremely important function is if, for example, you touch a live component and receive an electrical shock. There will be a sudden surge in current, and the circuit breaker can detect this and cut the power almost instantly to stop you being electrocuted and save your life. Okay, that's it for this video, but if you want to continue learning about electricity and electrical engineering, just click one of these videos on now and I'll catch the next lesson.
Okay. You might want to look at that again on your own time. Again, there are some simple questions. Current is the flow of electrons in one direction. To force electrons to move in a circuit, we need what do we need? Anybody? Everybody's muted. We need a voltage. Okay, anyway, look, it's you work on it. We're going to be back to this. There's more to be said about current. There's more to be said, especially the Ferris wheel analogy. But right now, current flows in one direction in the circuit. Does so because we have voltage of 130. Current is what it's all about. But the key to right now is to understand that the free electrons moving in one direction are already there in the wire. Okay. Okay, let's go back here. Are there any questions? All right, let's look at another one. Let's look at voltage now, and it's also the same engineering mindset, I think, which I like. The resistor one isn't, but this one is. Oh, look at this, pretty good. And we have how many? We have we have 15 questions here. And again, you might want to just look at the video a second time and answer the questions as you're looking at. Just stop the video and answer the questions. Let's see what we've got here. I don't quite know how long this one lasts. This is 10 minutes. Okay, let's look at it here.
Hey there guys, Paul here from the engineeringmindset.com. In this video, we're going to be discussing voltage. We'll learn what is voltage and potential difference, how to measure voltage, the difference between direct and alternating voltage as well as current, and finally we'll briefly look at why and how voltages vary around the world. In our last video, we learned that electricity is the flow of free electrons between atoms. Voltage is what pushes the free electrons around a circuit.
Now, there are two versions. I think he's going to mention this in a moment. There are two versions of electricity. The one we are associated with is the one that says current is the movement of free electrons in one direction. That's called the electron flow version. Some of you may, especially from physics, may be familiar with what's called the conventional current flow, which is the absence of free electrons or holes, and it moves in the opposite direction from positive to negative. Forget that now. We're going to talk about electrons flowing from negative to positive on the voltage, the electron flow version.
Without voltage, the free electrons will move around between atoms, but they move around randomly, so they aren't much use to us. It's only when we apply a voltage to a circuit that the free electrons will all move in the same direction, causing current. It's easy to imagine voltage like pressure in a water pipe. If we have a water tank completely filled with water, then the mass of all that water is going to cause a huge amount of pressure at the end of the pipe. If we have a water tank that's only partly filled, then there will be much less pressure in the pipe. If we open the valve to let the water flow, then more water will flow at a faster rate from the higher tank compared to tank. Same with electricity. If we have, then the current can flow. Voltage can exist without current. For example, we can measure the pressure in the pipe with the valve shut with no water flowing, and from this we can tell that the pipe is pressurized. What we're really measuring is the pressure difference between what's inside the pipe compared to the pressure outside. The same thing if we have a battery connected to a circuit with an open switch. The voltage is still present, we can measure that, and as soon as the switch closes, it's going to push the free electrons around the circuit.
Push and pull.
We sometimes hear voltage referred to as potential difference. This really means how much work can potentially be done by a circuit. Coming back to if we same level to do what isn't flow, but if we rate higher than the other, then this high now has the potential to flow down to the second one. And if we give it a path, then it will flow. If we place a turbine in its path, then we can use its energy to power a light or even an entire town. Back to the electrical circuit, this battery has a potential difference of 1.5 volts between its negative and positive terminal. If we connect a piece of wire to both terminals of a battery, then the pressure of the battery will force the electrons to flow in the same path.
Now, this is an interesting issue. We can do this. You can do this. I don't recommend that you do this for two reasons. But this is a complete circuit, and current is flowing through the wire, just as he said, pushing and pulling, or repelling and attracting those electrons. There are two problems with this circuit. Number one is that the resistance in the circuit is so low in the wire that so much current will try to flow that it will burn up the wire or burn up the battery. This is called a short, and it's because there's a shorter path for current to flow, meaning an easier path for current to flow, too easy, and it will burn up. The other problem with it is, why in the world would you want to do this? By that I mean, what use is it? There's no light bulb here, there's no motor here, there's no load here doing useful work. In other words, this is a circuit that is meaningless. It has no value for us as human beings, even if it didn't burn out.
We can then place electrical components in the path of these electrons to do work for us.
Okay, so the light bulb, one of the greatest inventions of all time, says, put some current through me, through my wire, inside the light bulb, and I'll produce heat, and more importantly, I'll produce light. That's what it does. You put a motor in there, the motor says, put some current through me, and I'll start spinning. I'm a device that changes electrical energy into mechanical motion.
For example, if we place a lamp into the circuit, then this will light up as the electrons flow through it. If we then added another battery to the circuit in series, then the electrons will effectively be boosted by the second battery because they can only flow along this path and there is more energy being added.
So in voltage sources like this, it put in series voltage sources added. So there's 3 volts now in this circuit. And as we've just seen before, the more voltage, the more current, the brighter the light.
This will combine the voltages so we get 3 volts. More volts equals more pressure, which means more pushing force. That will mean more electrons will flow and the lamp will glow brighter. However, if we were to move the battery and connect it in parallel, then the path of the electrons splits. Some will flow to the first battery and some will flow to the second battery. Therefore, the batteries will both provide the same amount of energy, so the voltage isn't combined. The voltage isn't boosted and we only get 1.5 volts. So the workload is split by the batteries and the lamp will be powered for longer, but it will be dimmer. We've covered this in much more detail within our electrical circuit series. Do check that out. Links are in the video description below. We measure the potential difference of voltage with the units of volts, and we use the symbol of a capital V to show this. If you look on your electrical appliances, you will see a number next to a capital V indicating how many volts the product is designed for. In this example, the manufacturers of this USB hard drive are telling us that the device needs to be connected to a 5-volt DC or direct current supply, and it needs 1 amp of current for the device to work. The term volt comes from an Italian physicist named Alessandro Volta, who invented the voltaic pile, which was the first electrical battery that could provide an electric current in a steady rate in a circuit. Voltage and volts are different. Remember, voltage is the pressure and volts is just the unit used to measure it in. The same as we know the pipe has pressure, but we use units to measure this pressure, such as bar, PSI, kPa, etc. As we saw earlier, we can measure volts with a voltmeter. This can be separate or part of a multimeter. If you don't have a multimeter yet, you can pick one of these up really cheaply. I highly encourage you to have one in your toolkit. I'll leave a link in the video description down below for where to get one for a good price. To measure voltage, we have to connect to the circuit in parallel across the 2 points we would like to know the voltage or potential difference for. So for a single battery in a circuit, then we measure 1.5 across the battery, and we also measure 1.5 volts across the lamp.
That doesn't mean 3 volts. It means that the battery is producing 1.5 volts and the light bulb is using 1.5 volts, that 1.5 volts to push and pull current through it.
The battery is providing 1.5 volts to the lamp, and the lamp uses 1.5 volts to produce light and heat.
I just said that.
In a 2-lamp series circuit, we measure 1.5 volts across the battery, 1.5 volts across the 2 lamps combined, but 0.75 volts across the lamps individually. The voltage or potential head between the lamps to provide light and heat. The lamps are dimmer because the voltage is being shared or divided. Again, we'll cover this in more detail in our electrical circuits tutorials. So we saw earlier that voltage and volts are different. Voltage is pressure and volts is the unit of measurement. So what does 1 volt mean? 1 volt is required to drive 1 coulomb, or approximately 6,242 quadrillion electrons, through a resistance of 1 ohm in 1 second. That's still a little confusing. So another way to explain this is that to power this 1.5 watt lamp with a
We'll talk about wattage and how that's different than current and voltage later.
5 volt battery would require 1 coulomb, or 6,242 quadrillion electrons, to flow from the battery and through the lamp every second for it to stay on. To power this 0.3 watt lamp with a 1.5 volt battery would require 0.2 coulomb, or approximately 1,872 quadrillion 600 trillion electrons, to flow from the battery and through the lamp every second for it to stay on. If we try to use a lower voltage, the lamp would turn on, but it decreases in brightness as the voltage decreases. That's because there is less pressure to force electrons through it. Less electrons flowing, less light that can be produced. The lamp rated for voltage and current is a higher voltage, and the lamp will be brighter because more electrons are flowing through it. But if we add too much voltage and current, then the lamp will blow because too many electrons try to pass through at once. If we look at some typical batteries, we can see that this AA battery has a voltage of 1.5 volts, and this one has a voltage of 9 volts. These are sources of direct voltage, meaning the pressure it provides moves the electrons in a constant current in one direction.
And this is because the polarity of the battery doesn't change. As long as the polarity stays the same, then the direction of current flow will stay the same. If you reverse the battery, turn it upside down, reverse it, then current will flow, still be DC, but it will flow in the opposite direction. Again, current flows in a circuit in one direction if the battery voltage polarity stays the same.
Much like the flow of water down a river. We cover this in our last video on electricity basics, so do check that out if you haven't already. Links are in the video description below. Direct voltage is usually represented with a capital V with some dots above this and a small horizontal line.
You'll see this on your
You can
meter.
see an example of this on the multimeter for the setting we would need in order to measure the voltage in a DC supply. If we plotted this voltage against time, we would produce a straight line that is constant. It is directed in one direction. The voltage in our wall sockets is alternating voltage. This is a different type of electricity. In this type, the electrons alternate between flowing forward and backwards because the polarity of the circuit is changing, much like the tide of the sea. If we plotted this voltage against time, we would get a sine wave as it moves forwards and rises to its maximum and then starts to decline. It passes through zero, and now the current is flowing backwards, but it then hits its minimum and reverses direction again.
We'll talk about AC later, okay? It's still current. It's just that the polarity of the source is constantly going back and forth, so therefore the current is going back and forth and back.
This is usually represented with a capital V with a wave. You can see the multimeter here also for measuring AC voltage. The voltage at these sockets varies depending on where in the world we are. The majority of the world uses 220 to 240 volts, but North, Central, and some of South America, as well as a few countries scattered across the planet, use 110 to 127 volts. We can measure the voltage at our sockets and see that it actually changes slightly throughout the day as the demand on the electricity network varies. And we can do that using one of these cheap energy meters. Again, links in the video description down below. If you want one of these, you can pick them up fairly cheaply and they're a great device for your toolbox. The reason for different voltages around the world goes all the way back to the beginning when electricity first started being created. At first, no standardizations. Each distribution network had its own voltage and frequency for whatever their engineers felt was best. Eventually, over time, some companies grew and dominated the market, and so voltage and frequency standardized as their products and services expanded. Governments also had to step in and pass laws and regulations to help standardize their countries so that people could buy products easily, but also trade products with other countries. This is still a problem to this day, but it's pretty much too late to fix as everyone is now so reliant on their electrical devices, and we would need to replace or modify them all to solve the problem. For example, if we take a hairdryer from the US, which is rated at 110 volts, and we plug it into a wall socket in Europe, which has 220 volts, the hairdryer will burn out at full power because there is just simply too much voltage or too much pressure, and the device just can't cope.
No, I'm sure you know, you cannot do that. I mean, the socket's different and it won't let it plug it in. But if you could, that's what.
If we took a hairdryer from Europe and plugged it into a US socket, it probably won't turn on. But if it does, it's not going to be very strong. It's going to be pretty weak because there just isn't enough pressure for it to function. Some products can be used in different voltages though. You need to check the manufacturer's labels on the product to first see if the product has been designed to cope with different voltages. For example, this laptop charger shows that it can be used on voltages between 100 and 240 volts, whereas this charger is only rated for 220 volts or 240 volts. That's it for this thing you're learning. Then check out the, and I'll catch you then.
I know that's all we're going to cover, not quite long. It's rather short though on resistance. Are there any questions about this? All right, let's take a look at one more of the big three. And that, of course, will be resistance. And this is not the same company producing this, but it's okay. Another 25 points. A few questions here, just a few questions. You're going to draw a resistor, and you probably do it down here. It's going to ask you to draw a rectangle and fill it in with graphite. Fill it in with your pencil graphite. And then take your meter and measure along the line and see what happens. So you're going to use your meter here. You use your DMM. You'll explain how there. See what you can do. And of course, we'll talk about the meter, but it'll give you an introduction to it. But let's see what we're talking about here. I think this is much a shorter video.
Managing social media campaigns, Monday.com, easy. How easy? This easy.
3.5, less than 4 minutes.
Resistance is friction that electricity experiences while flowing through something. Resistance, or the lack of resistance, is used in circuits to control the flow of current. This circuit is not a very practical one. In fact, it can be quite dangerous to build.
So this is the one we showed just a little while ago. You see with a wire going out there. Yeah, burn out so little, too much current, and again, it's no practical.
This circuit directly connects the poles of a voltage source together with a single piece of wire. The reason it is dangerous is because the magnitude of electric current may be very large in such a short circuit, and the release of energy very dramatic, usually in the form of heat. Normally, electric circuits are constructed in such a way as to make practical use of that released energy in as safe a manner as possible. One practical and popular use of electric current is for the operation of electric lighting. This metal filament inside a glass bulb which glows white hot or incandesces with heat energy when sufficient electric current passes through it. Like the battery, it has two conductive connection points, one for electrons to enter and the other for electrons to exit. Connected to a source of voltage, an electric lamp circuit looks something like this. As the electrons work their way through the thin metal filament of the lamp, they encounter more opposition to motion than they typically would in a thick piece of wire. This opposition to electric current depends on the type of material, its cross-sectional area, and its temperature. It is technically known as resistance. It can be said that conductors have low resistance and insulators have very resistance to the amount of circuit with an amount of voltage supplied by the battery, as compared with a short circuit where we had nothing but a wire joining one end of the voltage source, the battery, to the other. When electrons move against the opposition of resistance, friction is generated. Just like mechanical friction, the friction produced by electrons flowing against a resistance manifests itself in the form of heat. The concentrated resistance of a lamp's filament results in a relatively large amount of heat energy dissipated at that filament. This heat energy is enough to cause the filament to glow white hot, producing light, whereas the wires connecting the lamp to the battery, which have much lower resistance, hardly even get warm while conducting the same amount of current. As in the case of the circuit, if the continuity of the circuit is broken at any point, electron flow stops throughout the entire circuit. In this circuit, the lamp will stop glowing.
Now, it's interesting where this break is taking place. The truth is, if the break takes place anywhere in that circuit, current doesn't flow. Because, and here's another statement about electricity that you'll want to think about. Current always has to have a place to come from and a place to go to. It can't just have one of those. It can't just have a place to come from. It also has to have a place to go to. In other words, it needs a complete circuit. And I'll deal with this a little later.
As before, with no flow of electrons, the entire potential or voltage of the battery is available across the break, waiting for the opportunity of a connection to bridge across that break and permit electron flow again. This condition is known as an open circuit, where a break in the continuity of the circuit prevents current throughout. All it takes is a single break in continuity to open a circuit. Once any break has been connected again, the continuity of the circuit is reestablished, and it is known as a closed circuit. In the next part of this presentation, we will look at the action of switches in a circuit.
Okay. Very good. I don't know. And make it funny, I think. You lay down graphite, you know, and have fun with it. And those who've done it have had some fun. Okay, so where are we? We're with unit. All right, so this is the third week. We've read this. Get started. We reviewed the solderless circuit board. Make sure you understand that, or hopefully you do. And we've looked at these three videos, these three exercises. Concentrate on those and get them into me as soon as you can. Try to make it, you know, a goal, let's say, to do the current today, maybe the voltage tomorrow or whatever. But let's get those in. And I love to see those come in. And then, of course, this one, which will be on the meter itself, though you will be using your meter to measure the resistance in the resistance lead there to get you warmed up. This is a full activity in which, worth 100 points, in which you are going to go and you'll have all these little components which you got in your bag, and you will measure. We're going to measure resistors, we're going to measure voltage, we're going to measure current, and then we're going to use the meter to nodes. We're going to use it to check transistors. I think it's about it. So, you know, it'll be a full shot on Thursday on that. Okay. Let me stop the share here. Get back to you. We have 23 students. Okay, half the number, but are there any questions? Somebody said, is it good to have a multimeter? You were given one. You were sent one. You should have it. If you don't, I'm just about out of, well, I'm just about out of them, but I'm not completely out of them. Well, I don't understand. If you got the components, you got the meter. If you didn't get any component, my God, if you didn't get a box with your components and stuff in it, please let me know. But none of them, you should have all received one. But you can get these meters for less than $10. But you were, again, this is the meter. You have two leads with it that come with it. And everybody got this one. One person, I think, got a yellow one that I sent out because I'd run out of these. So I found a 30 watt soldering iron will be fine. Mm-hmm. Anything from 30 to around 30, 20 to 40 watt would be fine at Harbor Freight. Yeah, sure, that's good. You just try it. Try it. Again, the soldering is fun, you know, just want you to get going on that and do that. As I said before many times, up until now, I just gave students some blank printed circuit boards, a bunch of resistors and integrated circuits and told them to solder for an hour. And that was a practice solder. This time you're getting a lot more. So just use it, enjoy it, have fun with it. And again, almost all of you turned in the sheet. Okay, so for a summary now, and let me just pull this together. What I'd like you to do, again, I want you to catch up by the end of the week. That means 8 assignments, eight altogether. 2 for week 1, and there are a few of you, just a handful, that have not done those. If you're with me now, please do those. 2 of them for week 2. Again, a couple of you have a few things to make up with that. Do that, and then get on with week 3 with the current, voltage, resistance, and of course the meter, which we'll talk about on Thursday. Okay, any questions?
No.
No? All right, well, good. I look forward to seeing you on Thursday. I mean, I'm a little concerned that We don't have that many. All right, well, I'll write a summary up and check the summary. Please check every day. Check the announcements, check the additions to the sections. Okay, if there are no other questions, we'll bow out. And again, I have another class coming up. But
Thank you very much.
you're welcome, Anastasia. Thank you. Anybody else? Okay, I'm going to end it.
How do we turn in the assignments?
What's that, Oscar?
How do we turn in the assignment?
How do you turn in the assignments?
Yes.
Well, okay. Yes, I noticed, Oscar, that you haven't turned any in yet. Okay, you send them to me. That's a good. I'm glad you do the assignment and then send it to me as an attachment. Send it to my email, my Valley College email, as an attachment of some kind. Can you do that, Oscar?
Yeah, because I did that with the first week assignments. I turned in both, and then I think you received them.
My records show that you haven't. I have in my other room. I have all the files on all of you, but I don't have anything for you yet. You want to send those again, please?
Okay, then we'll do.
Send those two, and then get on to the second week. And so, I want you to succeed. So let's, okay, you're here. That's good that you're here on the YouTube. And so go ahead and send those in, okay? I want to give you guys this 3 weeks to catch up. There are 4 or 5 of you who haven't turned anything in, but I want you to do it. I want you to turn things in. Let's go. Good, thank you. Any other questions? Anybody else? Okay, I'll see you on Thursday. Get those assignments into me. I love, here I keep records. I love to fill this sheet out with lots of assignments. See you later.